All right, so welcome back, everybody. Let's get started. Any questions about the project? Yeah. Say it again. So the question is, if you pass all the traces, the given traces, is it guaranteed that you pass the test in the on the autograder? Yes and no. Should be. I mean, it's not exactly the same as all of those. The autograder has some more gallows and branches, and basically loads and stores. I mean, in principle, it's very similar to the others. It's not like we're doing something crazy. So I've seen many people actually submitted theirs. Not many, but I think like around 30 people-ish submitted already, mostly successful, passing the test. But I've seen also cases that their code still have some bugs. So yeah, it's yes and no. You can actually test it. I recommend testing it further a little bit with your own test cases, especially for like branches and Jalor. But if you think it works, and then there's no problem of submitting and seeing how it works. You can submit it as much as you want. So submit it, see what happens. If it doesn't work, then go back and test it further. Okay, so today's agenda is I'm going to finish the branch prediction and talk a little bit about what we call Superscalar. And then in the second part, I'm going to briefly talk about your quiz and one example I'm going to go through as well. So last time we talked about a bunch of different things about control flow hazards and branch prediction. We talked about miss penalty first and said that basically what we can do is moving everything to the decode stage. And with that, we are essentially reducing our miss penalty, the penalty of incorrectly guessing the branch from 3 cycles to 1 cycle, right? And at that point, we were using the always not taken strategy. Then we said, okay, what we can do with this and improve the miss rate as well. So we start, our discussion on how to predict taken instead of not taken. And we said that basically this is slightly more complicated because we need the addresses, we need the offset as well. And that's where we define the BTB and the way that BTB is designed and the way that the BTB is updated and so on and so forth. And then basically with that, we kind of divide our scenarios into 2 groups of non-branch and branches. We said that essentially non-branches never had an issue because we only put things into our BTB only if they are branches. And for branches, also it's not like completely solve the issue for some cases. For those cases that we have seen it before and they have only one direction of going, our BTB is basically fixing the problem. This was our BTB. There was this notion of tag and index. The reason that we use tag is to make sure that the PC matches perfectly well with our address that we want to use. But we said that essentially instead of saving the entire address as the tag, we're kind of saying that okay, the first half is kind of not the first half. The first part is going to be used to address individual lines here. So we don't need to really store this. What we really need to store is this portion here, and we call that tag. And we kind of save a little bit in terms of space area by doing this trick. And this side is basically the address is always 32 bits, assuming that we are using the 32-bit version of RISC-V. And basically what we do is that at first we're gonna compare this tag with this address. This part is basically telling you whether this branch has been seen before or not. If the answer to that was yes, then we were basically going and load this address to our next PC. If the answer to that was no, it means that we haven't seen this branch before, so we need to ignore this and then use PC+4. That was the idea. Yeah. So the question is, how many addresses can be stored? That depends on the number of entries that are here. or in other words, this n bit, so 2 to the power of this n is number of entries. It's a design decision that when we are building the hardware, we make that decision. Usually in regular systems, we are talking about few kilobytes of memory, because that's typically is enough for having good performance. Yeah. Okay, so and then so that's kind of like, you know, where we kind of stopped. I very quickly go through this rest of these slides, but let me go through it one more time to make sure that we understand this. So essentially, if you think about all the control flow instructions that we have kind of like, you know, 3 different kind of, you know, control flow instruction. We have conditional control flow, which is essentially our branch equal, less than, and so on and so forth. We don't know their direction. They might be taken and they might be not taken. But the thing that we know about them is that there's only 2 possible, you know, destinations for them. It's taken to that direction, and if it's not taken, it's going to be PC plus 4. Right? Then we have unconditional branches, which means that they are always branch. These are our jals and jumps instructions. They're always taken and they always have only one destination address. And we said that basically this is what BTB is great for, because we know exactly where they jump and we know their direction. So that would be awesome. Call is kind of like, you know, a specific case of unconditional branches, right? It's always taken and it always goes to the beginning of the function. But the return is kind of like, you know, a special case of this indirect branches, which indirect branches, if you remember, is those scenarios where we had jumping to the address that was stored in RS1, in our register number 1, and we were adding it with some offset, and that was the destination. And since RS1 technically can get any number between 0 to 2 to the power 31 minus 1, or if you think about it as a sign value, minus 2 to the power 31 to 2 to the power 31, then essentially we can jump anywhere in the memory based on that value, right? So we have many different next addresses. They're always taken, but the destination address is really large. And then we kind of like, you know, look back at our current design, and with BTB, we kind of like fixed this issue, right? Fixed this issue. This wasn't an issue at all. We just designed this in a way that, you know, BTB doesn't like mess up with the rest of our instructions. For BEQ and for our indirect branches, we still need to think about what is the best way to do it. For branch equal, we kind of like half solved the problem, because we know the offset, we know the address right now, we just don't know the direction. For now, we are assuming that these branches will be always taken, but in reality, branch equal sometimes might be taken and sometimes may not be taken, right? So we are thinking about how to optimize this second part. So with always taken, we have 70% accuracy, but what we want to do is that we want to get near to like, you know, 100%, right? So so the solution for this is what we call a branch predictor. Branch predictor is basically it's an optimized version of what we are doing so far, which we always saying that, oh, we are always doing guessing not taken, or we are always guessing taken. What we are doing now is we are saying that, okay, if we see a branch, instead of doing always the same thing, let's actually just make a decision dynamically, make a decision based off the past history of this specific branch, and based off that say, oh, this branch is going to be taken, but I don't think this branch is going to be taken, or things like that, right? So basically what we are doing is we track the previous behavior of the branches, and based off that, we're going to make a decision based off this new branch, okay? And we call that the branch prediction. The early version of that would be something that we call branch history table, or BHT. This BHT can be actually added to your BTB because you already have the comparison, you already have the addresses and all those things. So what you can do is basically adding this additional column in your BTB, which all it does is just storing 1 bit. And that bit basically would be your direction. You can define it as if 0, it's not taken, and if it's 1, it's taken. So what we're going to do with this branch history is that the next time another branch comes in, we're gonna do the same thing with the tag. So this part is the same as before. So we have this value here. Instead of directly sending this to the mux, we're gonna add this additional AND gate here, which is gonna read this corresponding value here, whether it's 0 or 1, and it's gonna AND that with this value. If it was 1, then if this is also 1, then we get the 1. If this one is 0, then it's guaranteed that this will be 0. So why are we doing this? Because we are essentially saying that the last time we saw this branch, for example, was taken. So when we are updating our BTB, what we are doing is that we're going to write 1 into this BHT. If the last time we saw that branch, the branch was not taken, then we're going to put 0 here. And with this trick, we are basically kind of like applying the previous history of this branch into our system. So for example, for JAL instructions, we always doing taken, so we always put 1 here. So for JAL, we have the exact same functionality that we had before. But the interesting thing is when we have things like branch equal or branch less than, and those kind of instructions. For these, since the direction of this is dynamically changing, sometimes it's taken, sometimes it's not taken. What we do is that we are basically, if the last time we saw this branch is taken, we will put 1 here. If the last time we saw this branch was not taken, we put a 0 here. And the next time we see this branch, we basically rely on the past history of this branch. This history is very short. It's only 1 bit in this case. Well, this is something that we can rely on.
Would it always be 1 so that like a JAL will make sure to take the branch, or is it someone?
So the question is, what is the default value in here? By default, do you mean the value before we populate the table? Yeah. So before we populate the table, we usually don't even look at this. So we don't put the valid tag. The first time we see the branch, we put the valid tag there, and that would be the value. So for JAL would be 1, for branch depends whether it was taken or not taken. Let me change my battery real quick. Any other questions? Zero, but if you're adding it to the table, doesn't mean that it's taken already that we put it in the table. So once we are adding this VHT, what we are doing in addition is that now we are also updating this table with not taken branches too. So we are basically updating this table regardless of whether this branch is taken or not. If it's a branch or if it's a JAL instruction, we're going to update this table. Does that make sense? All right. Yeah, so like kind of like I'll also put a note here that essentially for all the instructions other than branch equal, this would be always take, right? So if you think about this branch history table, it's in a sense it's a finite state machine as we've seen in the controller as well. The way it works is we have a simple finite state machine with only 2 states: the taken state and not taken state, right? And the way it works is this: that if we are in the taken state, if we see the branch, we're going to predict taken. And we're going to check the outcome. And if the outcome is also taken, we're going to stay in the same state, right? So if you see a branch, first of all, we're going to predict, if we are in this state, we're going to predict taken. Oops. Taken. And the second thing that happens, we need to update our state. So during the decode stage, we're going to see whether this was taken indeed or not. If it was taken, then we're going to stay. If indeed it was not taken, then we have to switch our state from taken to not taken. So the next time we're going to switch from taken to not taken. So the next time the same branch comes in again, the same branch is here. What we're gonna do is that if we have switched to the not taken, we're gonna predict not taken. And again, if we see not taken as the correct outcome, we're gonna stay in the same state. If we see that this indeed was taken, we're gonna switch to the predicted state. Okay. So it's like a simple finite state machine. So for example, let's look at this example. Let's say we have a pattern of, so this would be our pattern for now. That just don't think about this. Let's say we have a pattern of some branches, and I'm giving you the patterns that are going to be taken for most of the time. Sometimes will be not taken, and it's going to be taken again. And let's say, for example, we start with state taken. Okay. The initial state is taken. So what happens when we see this? We are in this state taken, so we're gonna predict taken, right? And then since the actual outcome is also taken, we're gonna stay in the same state of taken, right? So we're gonna stay in taken. Then we're gonna see this, and we're gonna predict taken, and same story. We're gonna stay in the same state. And we're going to repeat that all the way until we reach to this branch. We're going to still predict taken. Then this branch comes in. And in reality, this branch is not taken. But since we are in the taken state, we're going to predict taken, right? So we're going to, for this one, we're going to predict taken. And we're going to see in the decode stage that indeed we made a mistake and this branch should have been not taken. So what we're going to do is that we're going to switch our state from taken to not taken, right? So we're going to switch our state, our FSM, to not taken. And then this branch comes in. This branch comes in. And what happens is that since we are in the not taken state, we're going to predict not taken this time. So we're going to predict not taken here. But in fact, this should have been taken, right? So we made a mistake again. So we have to switch back from not taken to taken. And then this branch comes in, and then this time we are in the correct stage. So we're going to predict not taken. We're going to predict taken again, right? So what happens here is that if you look at this, we're going to predict for all of these 10, we're going to predict 8 of them correctly, and 2 of them would be incorrectly predicted, right? So we have like around 80% accuracy of detecting this system, correct? And for this specific case, as you can see, the performance is not great, because if you're looking at an always taken branch, so if you, instead of like using this 1 bit of like taken not taken strategy, if you always say that, oh, this branch would be taken, then we would have actually had only 9. We would have had 90% accuracy instead of 80. Right? Because we would have predict all of these correctly. This one would have been incorrect, and this one would be correct too. So 90%, 9 out of 10, we were right. So our branch history is actually not doing very good in this specific case, because the amount of history that it remembers is just 1. And for those branches that's kind of like flip-flop between taken and not taken, this kind of strategy is not the best strategy. Is that clear what we're doing, like why we're using a FSM and how do we predict this? Anybody has any doubts of how we calculate 80% and 90%? Okay. So now that we know that this kind of helps but doesn't fully help, let's see actually how we can make it better. So to make it better, the idea is that, okay, how about instead of looking at 1 bit, why don't we expand it to 2 bits? So basically, we have a history of last 2 branches instead of just 1 branch, because that's potentially could kind of absorb some of these, rapid changes of taken, not taken. So we're gonna use what we call a 2-bit predictor or bimodal branch predictor. And the idea is exactly the same. We're going to use 2 bits instead of 1 bit, and we're going to put it in our BTB. And we're going to expand our FSM into 4 states, because now we have 2 bits, right? So what happens here is that we're going to divide this FSM into 2 halves. In the top half, we're going to always predict not taken. So for state 0, 0, and for state 0, 1, we're going to predict not taken. And for the bottom half, we're gonna predict taken. Okay. So if you are in state 0, 0 or 0, 1, we're gonna predict not taken. If you are in 1, 0 and 1, 1, we're gonna predict taken. And if you see what happens is we kind of like added a little bit of resistance, hysteresis to our system. So if you are in this 0, 0 state and we see not taken as the correct outcome, we're going to stay here and we are happy, right? We predicted not taken and in reality it was not taken, so that's great. But if we see taken, then we're going to switch from 0, 1, 0, 0 to 0, 1. We're going to just increment it by 1. So we only transition from 0, 0 to 0, 1, not to the other states, okay? And in this case, we also still predicted not taken, but we are kind of like saying it, this is a weak not taken. That one was a strong not taken. This one is a weak not taken. And then what happens afterwards is that if we see not taken and we predict not taken, we're going to switch back to 0, 0. So we're going to say that, oh, this branch was indeed not taken. So let's go back to this strong prediction. But if we see that, it's actually taken, in other words, if we see 2 consecutive takens, then it means that this branch really wants to be taken. So we actually switch from 0, 1 to 1, 0. So we are switching from weak not taken to weak taken. So this part is kind of exactly the opposite of this direction here. This is 1, 0. We are predicting taken. If we see taken one more time, we're going to switch to strong taken 1, 1. If we see a not taken, we're going to switch to this scenario here. Okay. So, and then if you look at this in the same examples that I gave you before, assuming that we're starting from like 1, 0 or 1, 1, you will see that the first time, for example, we are doing taken and we are predicting taken because we are in 1, 0. Since we have seen a taken, we're going to switch from 1, 0 to 1, 1. Then we see this one and see taken, so we're going to stay at 1, 1. Predict taken is going to stay at 1, 1, and so on and so forth. At this point, this not taken will come in, and we're going to, since we are in 1, 1, we're going to predict taken, which is incorrect. And then we're going to switch from 1, 1 to 1, 0, right? Then the next one comes in, and since we are in 1, 0, we're going to predict taken again, and we're going to switch to 1, 1. And then we're going to continue doing that. So looking at the predicted pattern versus the actual pattern, you see that our accuracy jumps from 80% to 90%. Still, it's not 100%, but it's at least better than the previous case. And the reason for this is we are kind of like, kind of having some resistance to just one outliers in our system. You have a question? The question is, what is the default state? The default state, I mean, generally, we don't have default states. Usually, you're seeing the branch at some point. When the program starts, you can think about the default state would be something random. We don't know. So for the first few branches, you might have some misses. But in long term, if you look at this pattern, that the few branches doesn't matter, right? Say it again. So it's kind of like ping-ponging between taken and not taken. So the question is that if you have a pattern of taken not taken consecutively, would this solve the issue? If you're in the right state, start from the right initial state, yes, then yes, that would solve the issue, right? You always say, so for at least for half of them, you're right. So for example, if you're in 1, 0 and you see taken, not taken, taken, not taken, and so on, what happens is that for the first one, you're going to predict taken, and you see taken, so you switch to 1, 1, right? And then the next one comes in, and you predict taken again, but it's not taken, so it's switched back to 1, 0. So again, you're gonna predict taken, taken, taken. So in this case, you will always predict taken, 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 versus it should have been taken, not taken. So we have at least 50% accuracy. If we go back to 1 bit, we had 0% accuracy in that case because we are always switching, incorrectly to 0 and 1, 0 and 1. Say it again. So if you start in a strong, this would be the same scenario. So if you start from here, we see a taken, we're going to predict taken, we see a not taken. And if you start from a strong not taken, it's going to be the same thing. We always predict not taken. In reality, it should have been taken. So it's kind of like, it's getting better. So this is, again, it's kind of like a bare minimum branch predictor in some sense. So it's not the best. But in reality, most of the branches performing fairly good with a 2-bit predictor, because branches are typically very biased, which means that they're most of the time, they're for some good amount of time they're taken and then they switch to not taken. So with this 2-bit predictor, we kind of like, add this additional 1 bit to kind of like, have that history. So it kind of like, this is actually a real world stat. So around 85 to 90% of the time, with just this 2-bit predictor, we have a good accuracy. Question? So the question is, the strong taken is 1 1 1 or 1 0. Is that your question? Uh-huh. So the question is that the initial state could be 1 0 or could be 1 1, right? For example, these are just assumptions. It doesn't mean that they're there. So if you are in 1 0 and you see a taken, you switch to the strong taken, right? If you are in 1 1, you are already in a strong taken and you see a taken, so you stay in your strong taken. In terms of the outcome, doesn't matter whether you are in 1 1 or 1 0. In both cases, you are sending out taken. So what the processor sees is either taken or not taken. The processor does not understand strong versus weak. It's just a terminology that we're using kind of distinguish between these two. Does that make sense? So there is no recommend. So the question is that any preference between whether we should start from 1 0. The answer is we don't have control of where we are at each given point. Because again, think about this as kind of like a continuous stream of branches, and we are looking at just one frame of the time. So basically this pattern, there are some branches before and there are some branches after. We're always looking at some like time frame in between them. So we don't have control over what is the initial state. All right. But of course, the downside of this is that we are basically saying that for every single entry in your BTB, now you need 2 bits instead of 1 bit. So we're increasing the overhead, but that is a good trade-off because we are getting better performance in terms of branch predictions. So the question is, okay, for example, this flip-flopping or for these like, more complex branch predictors, what can we do? And the answer to that is there's always better scenarios. There's more complex scenarios that we can do. But the good news for you guys is that we're not going to go further than this. So that's the place that we're going to stop. Branch predictors has been like really popular area of research for a good amount of like 10 years or 20 years, mainly between 19s to 2010 or so. We kind of right now we're kind of saturated, so we're not really having much better branch predictors. But to give you some idea of what is kind of like state of the art, the state of the art is kind of like using some form of complex pattern recognition, typically using some form of machine learning to detect the patterns of your branches, and then using more storage area to remember more history. Okay, so we are usually what we call is, instead of like having one level, prediction of 2-bit counters, we have another level of prediction on top of this, which kind of like, decide between groups of branches. So for example, we say, okay, we have these 2-bit counters, but instead of like having one 2-bit counters, we have many of these 2-bit counters, and then we have another history that decide which one of these we should use. Okay. And then use that 2-bit counter. In principle, all of them are doing the same thing at the end. They all use a 2-bit counter, but which 2-bit counter should I use depends on previous history and previous history of that history. Okay? Yeah. So the question is, how does increasing the number of bits helps? So beyond 2-bit counter doesn't really help you with flip-flopping, because the problem is mostly those branches that's kind of like, change their behavior quickly. With adding more is actually you're making the problem worse. So instead of like having a 3-bit counter, it's better to have 2-bit counter, for example, and then having a mechanism to switch between these two. So these days, what you will see is a combination of having more and more of these, and then having some form of complex pattern recognition in order to detect which of these counters to use. Okay, so we typically that's what we are using these days. There are some terminologies such as tournament, hybrid, and so on, which basically all it does is picking all of these different branch predictors and decide dynamically which one to use. One trick that we are typically using in computer architecture is that when we have different options in terms of like, oh, we have different, branch predictor technologies, different cache technologies, different replacement policy technologies, and so on. If you don't know which one is better, instead of like, go with one and statically like kind of like hard code that into hardware, we put both of them in the hardware or all of them in the hardware, depending on how many we have. And then dynamically, we're going to have a decision process, a decision-making mechanism to see which one is performing better and use that one on the fly. So for example, if you have a 2-bit counter, a group of 2-bit counters, maybe a fancy machine learning predictor and all those things, we put all of them in the hardware because putting things in hardware is not that expensive. And then we're going to have a dynamic decision mechanism to see which one is performing better, because we always have the feedback from the decode stage, right? So we always can see whether our prediction was a correct prediction or not. And using that feedback, we're going to say, oh, okay, this branch predictor for this specific workload that I have is performing better. So I'm going to keep using this until I see that the other branch predictor is doing better. So it's kind of like creating some form of a tournament or competition and then dynamically make a decision. Question?
Like, so far we have like 85% like branch predictions. How much overhead? How bad is it taking branch?
So the question is, how much overhead is this for this more complex systems?
No, it seems like a lot of work for like, like 10% of the time to get incorrect branch.
Yeah. So the question is like, what is this trade-off? Because we are kind of like reaching to 90%, and then now question is, does it really worth it to go to like 92% with adding lots of hardware? It depends on what you're trying to achieve. A branch actually has a noticeable impact on your performance. And what happens was, if you go way back in the lectures, we said that, with this Moore's law, kind of like, our growth in terms of like hardware was like so fast and significant. So we kind of like had this like big real estate of hardware that being relatively underutilized. So adding things that give you 2% over, 2% improvement wasn't that bad. So it was a good trade, at least at that time in 90s and early 2000s. Nowadays, probably not. So if you're like, coming up with this strategy that improved your branch prediction from 95% to 96%, everybody's going to first ask you, what is the overhead? What is the power overhead? What is the latency overhead and those things? Because we are reaching to that point that, there is not much area left on your chip to do these things. But at that time, you had plenty of area. So that was like, it was like really fertile, ground for like, adding things to your hardware. And that's what we did. We were very aggressively adding things to the hardware at that time. Okay. So if you guys are interested, there are lots of interesting, articles about this. I might share a few of them in CampusWire for those of you who wants to see what is the state of the art. And before kind of like, concluding the discussion on branch predictors, so if you look back at this, we kind of like solve this problem and this problem. And with the branch predictor and something like a BHD and a 2-bit predictor, we are we are fixing this conditional branch as well. The last thing that we didn't really talk about is these indirect branches for our returns and JALR, right? So let's quickly talk about those. And the challenge and the main problem that our current strategy with BTB doesn't work for them is that they have so many target addresses. So the idea of, oh, I seen this branch, so let's actually save the address into the BTB doesn't work because that's only works if you have one or two targets, right? So if you have only one direction or two directions and only two offsets. For JALR, even if you save the address, there is no guarantee that we're going to jump into that address. That address could easily be changed, right? So the BTB technology for JALR doesn't work. So what we should do instead is we need a different type of branch prediction and address prediction for JALR. I'm not going to talk about the JALR specifically, but a subset of JALR, special types of JALR are returns and calls, right? We have lots of returns and calls, and that's actually more common than other types of JALRs, right? Because every program that you write, there should be some function calls and there will be some return calls. So let's see, actually, we can quickly fix this. The idea of this to fix the return and call is that in addition to having a BTB, we have another structure called return stack buffer or RSB. What the return stack buffer is that we basically proposing having a stack in addition to our BTB next to it. And all it does is that whenever we have a call, we push the return address into that stack. And what all it does is basically whenever we sees a return, we just go into that stack and pop it from that stack. And the nice thing is that if you think about your functions, there is always, an order between the function calls and returns, right? So if you have call, then you will have return. And if you use the stack option, it's guaranteed that this return is for this call and this return is for this call, right? So if you use some form of stack in hardware to store these things, you're guaranteed to have 100% accuracy for returns and calls, because whenever you see a call, you push the return address into your stack, and then whenever you see a return, you just go and grab that from your RSB rather than your BTB. There are some complications of how do we detect that this is a JALR and that's not a JAL, but that's a tiny bit of additional thing that we need to do in our fetch state. I'm not going to go through that part, but assuming that we can distinguish between JALR and JAL, what we can do is that whenever we see a return, we're just going to go and pop the stack and use that value for our call and returns. Does that make sense? Yeah, and then the nice thing about this is that this is not a huge overhead, because essentially all you need to do is somewhere between like 4 to 8 number of entries for this RSB. So it's very, very tiny amount of additional overhead that you're adding to your system, because typically you're just, you probably you don't have very deep functions. You typically just, call different functions and then return them afterwards. So somewhere between 4 to 8 should be enough. There's a tiny bit of optimization that we do, that this last one, instead of popping it, we keep popping the same thing. And these are for recursive functions. I'm going to leave it for you to think about why we are keeping the last one for recursive functions. But you have a question?
Yeah, I was curious if this affects like the return address overwrite attack, because you're storing them in the hardware whenever you call the function. So you're not rereading the return address from memory. I don't know if that's an x86.
So the question is, would that help with buffer overflow in some sense, right? But think about the buffer overflow, what it does. So this RSB is, the problem with this is that this RSB is part of the same memory. And in order for the operating system to keep track of where your return address are, it just needs to follow a convention for the call. So that's why it puts the frame buffer and return address, and then the local variables and so on. So stack itself is just a concept that we use. It has a physical meaning, which is basically a combination of RSV, BTB, and all those things. But the way that it works is that all of them are part of the same memory. So if you can't write things to your RSV, then you can overwrite things to in your RSV as well. But you are kind of in the same line. So the idea of like having a shadow stack is exactly like that. So we have a different stack, like we have a copy of this somewhere else. And this is the one that is transparent to the user, but this one is not. It's only seen by the hardware. And what we do is like copying this one to the other one, and that's kind of like fixing the issue. So that's the kind of the idea of shadow stack to prevent buffer overflow. Yeah. But for the rest of you, it's a different thing about, different problem if you're interested about security of this. But for the performance issues, we use an RSV in order to fix the issue of call and returns. Does that make sense? Anybody has any questions? All right. So, and then again, you might ask, what about other types of jumps? Other type of jumps needs additional predictors, which again, we're not going to go further than this. If you're interested, search for branch predictors for indirect branches and see what you get. It's completely different train of thoughts and design for hardware, which is going to be too much for this class to go through. Okay, so just have this in mind that we are doing something for indirect branches, but generally it's very, very hard problem to solve. So we're not going to get like 90% accuracy similar to simple branches, but we can improve the baseline a little bit. Okay. All right. So that's kind of like it for our branch predictor. So that's kind of like finish our discussion on our pipeline simple in order RISC-V processor. As I told you, our main goal was to optimize the performance. And as you have seen, we kind of like use multiple different techniques in order to improve our performance. We use pipelining, and we saw that we can actually improve our CPI with pipelining. Then we ran into this issue of hazards and data hazards. So we started adding forwarding to the system. Then we ran into the problem of branch predictors and control flow hazards. So we add speculation and prediction to our systems. And that's where we kind of like, now we are, right? So we are kind of like, we can fix mostly all the raw data hazards problem. We can fix most of the control flow hazard problem. Of course, none of them would be 100% accurate, and none of them would be 100% fixing the problems. There are problems that fundamentally we cannot solve. And then, of course, we can always use the support of compiler and software. We didn't really go into the details of that. Very briefly talk about, for example, the role of the compiler on control flow. But keep in mind that compiler and software and generally algorithm design has a role on all of these things. If you take courses in operating system and compiler, you will see more details of that. Okay. So of course, now the next question is, can we do better than this? Because the story doesn't end here, and we always want to improve our performance. So we're kind of like halfway through our innovations in the golden computer architecture era. The second half is actually the things that we're going to discuss from now on in this lecture, next lecture, and next week. So in order to understand what actually we can do, let's go back to our pipeline design and our iron law and see what we basically pipeline stages gave us, right? So if you're adding more and more pipeline stages, that could be a simple thing to improve the performance, right? So if we add more pipeline stages, it gives us two things. One is it gives us smaller CT, and it keeps the CPI the same. So we're basically just improving the CT. So first of all, the iron law was like CT times CPI times IC. And adding more and more pipeline stages that we extensively discussed in this class keeps this CT the same. So this stays the same. IC, of course, has no relevance with the pipeline stages. So that one stays the same. Our CPI stays the same. our CPI stays the same, our IC stays the same, and our CT goes down. Why does it go down? Because we are breaking our critical path into smaller pieces, so we can actually, clock our design faster and faster. So our CT goes down. So it seems to be that adding more than 5-stage pipeline is a good idea. Why don't we do 10 or 20 or 100 or I don't know, whatever number that we can do? The problem with that is at some point we're gonna get to this point which we call diminishing returns. That adding more pipeline stages not only improve our CT, is actually decreasing our CT. Is actually increasing our CT. It means that the delay per stages it becomes higher and higher. The reason for that is 3 things. One is by adding more and more pipeline stages, we are adding more and more hazards, right? Because think about we have hazards between EX and ID, and we had hazards between write back and ID, and we had hazards between memory and ID. Now, if I add 10 more stages in between those, we have hazards between ID and all those 10 stages. So we need bigger muxes, we need more complex hazard detection units and all those things, because we need to forward from every single one of those pipeline stages back to our ID, right? So that means that we are adding more and more muxes, and as you see in your homework, for example, adding mux actually add delay to your pipeline, to your general data path. So at some point, this hazard goes so big that it doesn't really worth it to add more. Another problem is the complexity that we are adding to our controller, to our design is going to be so high that either we're going to have power issues or we're going to have delay issues because our controller becoming more and more complex. And finally, the registers itself, so these pipeline registers are actually adding delays, because if you remember, reading from your PC or reading from your any other register also has some read delays, right? So eventually, if you add lots of these, that delay becomes significant, and that delay will be added to your data path. So long story short, adding pipeline stages at some point helps, but at some point it's just going to be so much the overhead that comes with it that it no longer is worth it to actually add additional pipelines. So these, very complex state-of-the-art, Intel processors has somewhere between 10 to 20 pipeline stages. But not more than that. And even that 10 to 20 is like for very high-end processors. Most of the processors have somewhere between 3 to 10 stages of the pipeline just because of this issue. Okay? So adding pipeline stages kind of at some point stops. And if you think about this design that we have what is called a scalar pipeline processor or a scalar processor. By scalar, we means that at each given point, at each of these stages, we only process one instruction at a time, one data at a time, right? So our fundamental limit in designing a pipeline processor is that at best we can get IPC equal to 1, right? With pipelining and do all this overlapping and so on, we get IPC equal to 1. And in reality, as I told you already, our IPC is less than 1. Why? Because we have, for example, load use hazards that you need to stall your processor for 1 cycle. You have control flow hazards that you need to stall your processor for 1 or 3 cycles. So your effective IPC is not exactly 1, is in fact less than 1, right? But in best case scenario, if you assume that we have the best possible branch predictor and the best possible way of forwarding and so on, we're going to get to IPC equal to 1. And the only kind of wiggle room that we have is making CT smaller and smaller. So we still get faster processors, as we already doing that even now. But we cannot really jump to much higher performance processors. We only have whatever the transistors are giving us in terms of CT, and that would be the performance that we can get. Okay? So you can immediately think that, okay, what if we are doing multiple instructions at a time? So for every single pipeline stage, instead of doing 1, why don't we do more than 1, right? And this is basically what it comes from, what we call instruction level parallelism, or ILP. The idea is we want to have multiple instructions at every single pipeline stages. For example, if we can do 2 instructions at each pipeline stage, our CPI effectively becomes half, right? Becomes becomes half. The cycle per instructions, because for every cycle we're finishing 2 instructions, so our cycle per instruction becomes half, or our IPC becomes more than 1, right? Becomes like 2, which is good. Which means that our timing for finishing this program becomes smaller and smaller. If you look at the different part of parallel processing, instruction level parallelism is actually a portion of a bigger scheme. We have bit level parallelism, which is BLP. We have instruction level parallelism, which essentially tells you how to run multiple instructions at the same time. And then we can also have higher level of parallelism, which is task level and data level parallelisms, which when we actually reach to the multi-core system, you will see that how we actually get into those parts as well. But this instruction level parallelism, what it does is basically telling you that instead of having a scalar processor, let's have what's called a superscalar processor, which essentially all it does is that for each stage of the pipeline, instead of just getting 1 instruction at a time, we're getting multiple instructions at a time, okay? So let's see how we can do it. Just very simply and very basic, what I'm showing here is the same pipeline stage that I show you, and I added this red part to it, which what it does is basically, making our system able to handle 2 instructions at a time. There are a few things that you can see here. So first of all, we cannot copy all the things twice, right? For example, we can copy the ALU twice to kind of like process 2 set of instructions at the time, but you cannot copy the memory twice because memory is just very expensive to copy, okay? So there are some limitations with our superscalar. It's not like, we're gonna copy everything twice and then we're going to just have a perfect superscalar processor that has 2 instructions at a time and that's it. Things like register file or data memory or instruction memory cannot be copied, right? Because we have limited amount of memory anyway. But there are things that you can modify, right? You can, for example, read 2 instructions at a time, right? So instead of reading 1 instruction, you can have 2 ports in your instruction memory and read 2 things at a time. You don't need 2 PCs because you can do PC and PC plus 4. So instead of reading 1 instruction, reading instruction that points to the PC, you can read instruction 1 that points to PC, and then read instruction 2 that points to PC plus 4. Okay, so all you need to do is just generating PC and PC plus 4. So you need 1 register, 2 numbers, but this way you can read 2 things at the same time, and then you basically have 2 instructions at the same time. Then your register file doesn't need to be duplicated, but all you need to do is adding 2 more read ports and adding 2 more 1 more write ports and adding 2 more RS1 and RS2. So basically you will have RS1 and RS2 for the first instruction, and you will have RS1 and RS2 for the second instruction. Okay, these might be the same thing, they might be different. Okay, so we are basically saying that we are duplicating this in order to read more registers at the same time. Yeah. The question is, what is schematic convention? Is that what do you mean by what schematic? It's very similar to what we've shown before in terms of mem. Then we show you like mem is fetch, decode, ALU and so on and so forth. Yeah, instructions. No, there's no name. It's just something like random that we came up to. This is instruction cache in some sense. It's the same thing. So going back to what I was going to say is that we are basically adding more read ports. But these things, all of these additional things that we are adding are coming with some overheads. It has power overheads because adding more read ports or write ports has lots of power overheads. And it has, of course, area overheads because we are essentially saying that instead of like having 1 ALU, we are duplicating our ALUs into 2 ALUs, right? So it comes with some overhead, but the nice thing about it is we can technically get to IPC equal to n, where n is basically the number of lanes that we are adding to our processor. So for example, if you look at this example here, our load and add goes into the instruction mem together. Our load and add goes into our register file together. Then we can fetch sub and add I here, and then this story continues. And what we can see from this side is as if that we are finishing two instructions at the same time. In other words, our IPC would be equal to 2, or our CPI would be equal to 0.5, right? And then with the iron light means that our processor performance would be doubled if we have n equal to 2. And now think about, okay, why don't we stay at 2? Why don't we do 4 or 8 or 16 and so on and so forth? So what we're saying is that you just replicate and make your processor bigger and bigger, more parallel lines to each of these, different units. And with that, you probably can potentially get into higher IPCs. Any question here? So what would be the problem with that? The problem with that would be dependencies, because when you want to send two things at the same time into the pipeline stages, you no longer can use forwarding because they're at the same stage together. So it's not like, this one is the previous or this one is the next. They're going at the same time into the same pipeline. So you cannot have dependency between these two instructions. So you cannot have things like raw data hazards. You cannot have control flow hazards and any of that, right? Because these two going together at the exact same time, so there is no differentiate between these two. So what it means is that we need to find a mechanism to kind of like find these independent instructions and send them together. And unfortunately, that would be a difficult thing to do because we need to do lots of checks. So for example, for two instructions, we need to check source 1 with destination 1, source 2 with destination 2, then source 1 with destination 2, and so on and so forth, because we cannot like put things together if the destination of this one is source of the other one, because there is a raw data hazard. So we need to check for raw data hazards. We need to check for control flow hazards. And this exponentially grows as we add more and more number of pipeline stage, more and more lanes into our superscalar. So for example, for 4, we need 12 checks. For more than for 8s, we need lots of checks. Okay, so that would be a big problem that we're going to have in a superscalar processor. And again, at some point, we're going to have the same issue with the pipeline processor, that adding more lanes to our superscalar not only improve our performance, but in fact actually reduce our performance, because we're going to have a diminishing returns into our system, because we don't have enough instruction to send it to our pipeline stages, because all of them are kind of dependent to each other. So we can maybe only have 2 or 3 or something like that. Okay. So to kind of give you a big picture about the superscalar, the trade-off in superscalar is that superscalar, for example, something like n equal to 4, which is actually what is being used regularly in our modern processors. So you probably have heard the word 4 issue, like Intel Core i7 4 issue, something like that. That number 4 is basically this, referring to this n, this superscalar lane. What your superscalar processor gives to you is potentially higher IPC, potentially better performance. Ideal scenario, if you're adding n lanes to your processor, you get IPC equal to n. So you improve your performance by n times. In reality, there are two problems. One is the complexity that you're adding to your system. And the second is, because of the dependencies, you cannot utilize all of your lanes at the same time. So your effective IPC is usually much, much less than what you would get in the ideal scenario, because you cannot really, if you have, for example, a branch instruction, you cannot really put anything else with it, because you don't know whether this branch is going to be taken or not taken. So you cannot really run things with it, right? So problems like this would be what we're going to have with the superscalar processor. Any questions? Yeah, so basically, as I said, we cannot have a full pipeline. By full means that all the pipeline stages are occupied and all the lanes in those pipeline stages are occupied, mainly because of these stalls and the dependencies. Okay. So, and then if you add this to what we're saying, the main reason that we have this kind of problem is that we're kind of limiting ourselves to the instruction order. We're saying that, okay, either I'm going to put these two in my superscalar, or if I cannot put this one into my superscalar, I'm going to put this one into the superscalar and wait. And once this is done, then I'm going to put maybe these two together and so on. So, right? So when we are limiting ourselves to this, we are fundamentally limit ourselves to how we can use our superscalar. And that would be the problem that we're going to have with this type of design in our processor. And the solution to that is what we're going to discuss next week about out of order execution. So you're going to present a fundamentally different approach to look at our instruction sets and our instruction mix and tell you how with ideas like superscalar, which we have like maybe 4 or 8 different lanes to put instruction in, how we can combine this functionality with our pipeline and superscalar, and then look at the list of instructions and large list of instructions, because we're talking about hundreds and hundreds of instructions that needs to be executed, and show that how we can then search through those and always fill our pipeline with independent instruction that way. And not only that, we can show you how we can hide the stalls and the delays that cause with this dependencies and so on with something like out of order execution. Okay, and that's where we're going to have a significant jump in terms of performance, because we're not only just going to limit ourselves with IPC equal to n, we're going to actually jump further than that. All right. Okay, let's have a quick break and then come back and we're going to talk about the quiz. Oops. Okay, let's quickly go over what you should expect for quiz 1, and also go through the example that we gave you on the website. Anybody has any question before we get started about the project, about the lectures in general? Are we good? Okay. So the quiz would be in person. You have to come here. There is a sign-in sheet that you have to sign your name. So make sure before you're leaving the class, your name is there. If your name is not there, even if you submit your quiz, we're not going to grade it. Okay. And the way we're going to publish the quiz is that then we're not going to hand you paper copies, because there are lots of you and there are lots of papers. What we're going to do is that we're going to post it on a Google Doc and share the links on the website. So feel free to bring your laptop if you want. Otherwise, you can just see it on your phone, or we're going to display it here and you're going to see it and you're going to write it in a piece of paper. You can also do everything online using your tablet or your laptop and submit the online version. That's totally fine by me as well. You have to submit it on Gradescope. So either take pictures, similar to the way that you submit your homeworks, take pictures, or just save it as PDF and submit it to Gradescope. Okay. Yeah, as I said, you can use your laptop and tablets, or if you're like a kind of piece of paper person, you can put things on the piece of paper. Just keep in mind that there might be some like drawing and redrawing of data path and so on. So think about what's the best way, what's the most efficient way for you to doing that. You can also do a combination of typing things on your laptop and writing in a piece of paper and take a picture and add it to your file as well. So whichever you think is the best, that's fine by us. The only requirement is that it's readable, so we can actually grade it. So there will be a grader that's going to grade it. Yeah. So the question is, how is the uploading to the Gradescope will work if the internet is messy? That's a good question. I'll think about it and find a way. In worst case, you just hand me your paper copies at least, and then I'll upload it later, or you just take a picture of it and have it as kind of like, you can send it later. Just if it's timestamped correctly, I'll accept it later as well. What we will try to do is that we make the exam somewhere between 60 to 80 minutes. So we're gonna have like at least a 10-minute buffer for you to upload things, hopefully. So that should be enough, hopefully, if this works. But if it doesn't, then we will do something to figure it out. The question is, if you're planning to write a data path, whether is it better to do it in a piece of paper or tablet? Either is fine. You can always take a screenshot and save that with the time, and I can see that that's actually like right time. So as long as it's timestamped, even if you didn't upload it on Gradescope in time, I'll let you guys to upload it later. Say it again. Oh, the question is, will we have lecture on Tuesday or just be the quiz? I'm probably gonna just give you a 15 to 20 minutes short lecture as the intro to Out of Order, and then start the quiz. Okay. Yeah, so as I said, somewhere between 60 to 80 minutes, hopefully. In terms of material, would be everything from lecture 1 all the way to end of lecture 7. In lecture 7, we talked about control flow and control flow hazards and branches a little bit. All you need to know for quiz 1 is what control flow hazard is, what is the problem with branches. You need to know that. You also need to know that if we have a branch in a pipeline processor, what should we do? And at that point, the only thing that we could have done was stalling the processor for 3 cycles, okay? So your information about branch is, at that point, was the branches cause a control flow hazards, and in order to fix that hazards, we need to detect them, and we need to stall the processor for 3 cycles, okay? So if you see a question about that, that like has control flow hazards in addition to other hazards, your solution, your assumption should be that we need to stall for 3 cycles. I'll probably, if we have some question like that, we will specifically mention that. So all these things about branch predictors and moving things to the decode stage and having BTB and all those things, not going to be included in your quiz number 1, okay? It is open book and open note. I have lots of questions in CampusWire time and time again. You are allowed to bring anything you want in the class, or your notes, your previous notes, lecture slides, recordings, books, anything you want, you can bring it. I don't care if you want to bring this many books, you can. You can even search things online. You can look at the lectures. You can use any software, or if you want to compile it or disassemble it or run it through your own software. If you want to use a calculator, if you want to, I don't know, convert binary to hex using an online tool, you can do all of those things, okay? And you are allowed to search internet. So if you have no idea what is pipeline, you can just search what is pipeline during the exam. What is you're not allowed to do and consider cheating, and we will, if we catch it, we're going to report it, and you're going to face actions based off that, is that you're not allowed to talk to each other during the exam. You're not allowed to send texts, given that you're working with your laptops or tablets and phones. You cannot share or ask or anything regarding the quiz or anything else during the time that you are here. You can also not post questions online or anything relevant to that online, or asking any question on Reddit or Chegg or or Discord or anything like that. So you're not allowed to post any question actively. You can only use the existing information. So if you find a Reddit post that already talk about this question, then great luck for you. Good searching skills. So you can use that. That's totally fair. But you cannot actively post something on Reddit and saying that, oh, I'm in this quiz and would be helping me with this pipeline question. Okay. In terms of asking question during the exam, you can ask question from me or from the TAs. I think both of the TAs will be here. The easiest way of asking us question is that if you're kind of like accessible, like sitting in this like in the end of rows or in the front seat, just raise your hand and we're going to come to you and answer your question. If you're somewhere in the middle, the easiest way to ask question is just send us a message on CampusWire. Just type your question in on CampusWire, and I'm gonna regularly check my laptop standing here or going answering question and come back and check my CampusWire. Okay, so you can easily put your question in CampusWire. If you're not bringing anything and you really need to ask question, then raise your hand and we find a way to get to you and answer your question. Okay, but the easiest way to have the limited amount of disruption to anybody else is just type your question in CampusWire. Yeah. So the question is how many questions we're gonna have? Either 2 or 3, but at least one of them would be multiple, like part question, like do this and that, and what will happen if you do this and things like that. Yeah. What if the Wi-Fi crashes? Another question is that we're going to show it here first of all, but another thing is that once you get the question downloaded and have it offline as soon as possible. Again, we're going to have a little bit buffer at the beginning and end to have kind of like combat these kind of issues. In the past, we also have seen this problem of like once we share the link, like 100 people try to like read that in their Google Doc, and usually Google Doc server is like gets really slow. There are these problems, but don't get like frustrated or panicked. It's gonna be like 5 minutes later, and you will have plenty of time to compensate for that. Okay. If things go horribly wrong and then like the Wi-Fi completely crashes, and we large number of people couldn't really submit theirs, then we will of course have to redo the quiz for those people or find some other ways of doing that. Hopefully it won't happen. Now that I know that there are going to be more Wi-Fi issues, I might actually have the PDF as well ready and just put it there, or at least send a Bluetooth or something like that for you guys, or at least have some paper copy just in case and then send it to you. Yeah. That could be. So the question is, can I give you an encrypted PDF and then give you a password? Yeah, that could be also a nice, yeah. Or zip it and then send it to you. But it would be like, everybody did it before trying to break. It's like searching online. How do I find? Yeah, I have to. Yeah, we can probably do that too. The reason that I usually go with Google Doc is that sometimes there are some errors or somebody asks a question and then I want to clarify it in the text. So I just quickly go and change it. But now that's given the great, infrastructure that we have at UCLA, maybe we can change that this time and just have like a hard. But yeah, that could be a good idea. Let me think about it and maybe send it to you. At least an hour before, something like that. I can release it so people can actually download it and then come into the class. Okay. Any other questions? Are we good for the quiz? Yeah, you have to be physically in this room. Yeah. But it will be online, but you have to be physically here. Okay. That's why the signing part is coming to play. Yeah. That's why you have to sign your name physically here. You can bring a double gang, like a dummy person here, and then You submit yours. That could be also. You need someone here that writes your name. Yeah. Any other question? Yeah. Okay. Let's actually go through this example that I gave you, given that we didn't really go into the pipeline question. Potentially one question that you might see in the quiz would be something like this, that we give you a list of instructions and we ask you to give us like the timing of these instructions in a pipeline fashion, if a 5-stage pipeline. And for example, this is like the question that we gave in the last year's quiz. And we said that, for example, let's assume there's no forwarding and the branches are resolved in the mem stage, then just fill the pipeline. And one thing you need to, so your pipeline basically would be, fetch, decode. Like you have to put like things like F, D, E, M, and W in the table. One thing you need to, like for these type of questions, of course, what you need to know is things goes one cycle by one cycle unless there is some form of hazards and we need to stall the processor. The type of hazards that you need to be worried about is raw data hazard, load use hazards, and control flow hazards, right? These 3 things. If we have forwarding, we can fix some of them. For some of them, even with forwarding, we cannot fix them, so we have to stall the processor. So for example, in this case, our ADI, so if this is 1, 2, 3, so on and so forth. So our ADI goes into the pipeline. Then our ORI goes into the fetch, goes into the decode. You have to check whether there is any dependencies between here and here. There's not. So the ORI can continue, right? Then the ANDI comes in, and ANDI has dependency with ADI. So what we need to do is that the ANDI goes into the fetch, goes into the decode, but it cannot go into the execution stage. Remember, we don't have forwarding, so we need to wait until the end of we need to wait until the write back stage is finished. Keep in mind that whether we are saying that we have half cycle or we don't have half cycle, the default is we do have half cycle, so you can assume that there is half cycle. So in that case, you can stays in this decode stage and then goes into the execution stage in this next cycle. Because remember, if we had half cycle, we had forwarding here and we were done. But since we don't have forwarding, we need to stay one cycle and then move forward, right? So for ADI, we would have F, D, D, E, M, and W, right? And then for our sub would be F here. Since D is kind of stalled, F has to also stall, and then goes into the D now that the stall has been removed. You have to check whether you have any other data hazard here or not. You have a potential hazard here and here, but this one is already done, so you're safe to go here. So you do E, M, and W. This is for SOP, right? And then you have the LW. LW gonna use X5 as the destination register and X0 as the source. So no data hazard here. So this is gonna be fetch here, the code here, execution. Oops, sorry. It's gonna be fetch here, the code here, execution, memory, and write back. If I'm making a mistake, just let me know. Might missing something. And then we have a big problem here with load and add, which we have a data hazard because this is basically the destination register for load, and then we have a source register for X5. So we're gonna fetch here, we're gonna decode here, then we have to stay for really, really long time. So we're gonna have decode, and then go to another decode, and then I think execution, memory, and write back, right? Because the add cannot finish until we actually finish the write back stage and then continue, right? Actually, sorry, this would be execute, memory, and write back, because we have the half cycle, right? So once we do the write back, we can decode. So far, so good? Yeah, question. So the question is that if we have the half cycle, why don't we execute within the same cycle with write back, right? If you have forwarding, you can do that. If you don't have forwarding, you should decode and write back Yeah. So the default was, when we were saying that, we were talking about forwarding. Now we are specifically saying that we don't have forwarding, right? So. But yeah, the default is you have forwarding, so you can do write back and execute in the same stage. Any other questions? Yeah. Yeah, you can either use this or using it this way. We accept both of them. I think for me it's more clear to doing this way. The question was, like, I think the question said use this like a dash to show that there's a pipeline, there's a stall. What I did here was repeating the same character over and over. Both of them are acceptable. Even if you look at the solution, we said that kind of both of them are kind of okay. Yeah. Why do we want to? Oh, because the fetch is in. So the question is why we have two fetches for sub, because in the fetch we have stalled the processor. So since the previous instruction is stall, the fetch also stays in the same cycle. So you don't fetch twice, the fetch just stays in the same cycle. One thing you could have done is this, right? Or this. So we are basically saying we don't do anything at that cycle, we're just staying there.
We're using X0 if you're as a right to.
Mm-hmm.
That case, if you're using X0 as the operating for X0 is
yeah. So the question is, if you have an X0 as destination, and then in the next few cycles you're using X0 as a source, does it apply the same data hazard as the other registers? And the answer is no. X0 is always 0. So during your check, you have to be careful that X0 is not. You shouldn't consider X0 as your raw data hazard. Even in the lectures, I think we said that those checks should be like if this is equal to that, and like RS and RD are not equal to 0. Yeah.
For the solve instruction, instead of fetching it and then having it solve the fetch stage, we instead just like wait to fetch it, like wait.
So the question is, for the sub instruction, instead of fetching it and then stalling, why don't we just don't do anything and then fetch? The answer is, like, fetching is a combinational activity, right? You have the PC and it's just a wire that gets activated and goes into the memory and read things, right? And we don't have like a mem read for instruction memory. So it's not something that you can control. It's just logic that propagates through your circuit. It doesn't matter whether you don't do it or you can. There are techniques such as power gating that you like completely disable that stage. We're not going to go through that part. So yeah, we just basically fetch. You can think about it as two things. Like either we fetch it over and over, the same thing happens, or we fetch it one time and the second time you just say don't do anything. Well, either of these two. Okay, where are we? Add, okay, and then I think the branch equal then comes in, right? So the branch should come here. Then we have to stall the branch. So we either use, this or this, stays here. Now that the decode goes into execution, now the branch is clear to go to the next stage. Again, we have to check whether we have a raw data hazard, and there is a raw data hazard. It's a tricky one because X5 here is also a source, right? So it's not a destination. And it's actually being written by the add here. And it's also being written by the load. So it's double tricky in some sense because you not only have to wait for this one, you also have to wait for this one. So kind of two type of stalls. So obviously we cannot like move forward. We cannot move forward. And this is the point that we can move forward because we need to wait for this add to finish, right? And we are saying that we are basically skipping this instructions, right? But what happens is we are basically, as soon as we see a fetch here, we're gonna fetch the next instruction, and we're gonna stay here. We're gonna stay here as well. Remember that the branch, the outcome of the branch is known at the end of the mem cycle. So this one has to stay all the way until this point that this one reaches to the write back stage, and then we can actually fetch the correct one and then decode this one and so on. So these are actually, all of them are fetching garbage, and your multiply, which is this instruction here, is really correctly being fetched at this cycle. So the way that you can show this is either showing this and say, oh, these are all garbage, and our multiply is actually really starting here, or you can just use it this way and say that this is actually the correct one. There are some questions, yeah. Say it again, this line? So this is for this last instruction, mul instruction, because we have a branch. So the question is, what is this line? So we have a branch. So if you look at this instructions, you see that we have branch, and we are saying that this branch should be taken. Okay. What it means is that these things that we're gonna fetch here is gonna be garbage. We're gonna throw them all out, and in reality, we need to fetch really this. Oops. We really need to fetch this mul instruction, which is, I mean, we haven't covered multiply, but just some random instruction, whatever this is, okay? So what I'm showing here is at this point in the branch, we need to fetch something at this point, right? At this point, we need to fetch something. That something would be ORI probably, right? Depending on how this processor works, but we don't care because at some point we're going to fetch the correct thing, and we need to just show the correct cycle for that. So here, and here, and all the way, this 5 fetches would be either stalled or incorrect fetches. At this point, since we are in the write back stage of the branch, we know the correct outcome, and now we can fetch the correct instruction. So our mul really starts at whatever this cycle is, I think 20 or 21 or something like that. Does that make sense? You can leave it blank. Yeah, the question is, can we leave it blank? Yes. Yeah. So the question is that, would the correct fetch comes after the write back? So remember, for the PC, the results of the PC was known in the memory stage. So at the write back stage, we have the forwarding, and we have the half cycle, and we have the correct value. It's not forwarding that fixed this problem. It's the half cycle that fixed this problem, right? Yeah, because if you remember, this is not the raw data hazard. This is a control flow hazard. Anybody else has a question? Yeah, go ahead. Yeah, so the question is, what happens here? So at this point, the PC will be written in the half cycle of this, right? And then in this second half cycle, the fetch gets the correct value of PC and then feed it into the instruction memory, and we get the correct value, right?
Why is there a stall before the decode?
But after we put it, not a stall before this, like, shouldn't the D and the stack.
So the question is for and I, why do we have decode and stall and not slash and like not showing it the other way around? It's actually my TAs were kind of like, had this debate together, and they're each of them would want the other notation. Both cases are the same thing. That's why I kind of prefer D and D, because in reality at both stages you have D. It's just at the first stage you have an invalid or garbage D, and in the second stage you have a correct D. But either of those notations is fine in terms of just showing them. So if you're assuming that by dash I mean garbage and by D I mean correct, then what you're saying is right, dash and then D. Another way of thinking about this is that the decode happens and dash means just the repeat of decode, and that's why there is a dash. Either of these, like if you do DD or dash D or D dash, all three are kind of acceptable based off your way of thinking. Any other questions? Okay. So I think that's it for this one. Yeah, just be careful about all these different data hazards between the half cycle and not having half cycle. Some of them are half cycle relevant, some of them are not half cycle relevant, and so on. Okay. Then in the second part of the same question, we asked for what if now we have forwarding, and now what if we have resolved the branches at the decode stage. At that point in that quiz, we already covered branch prediction, and that's why we had that. Probably for this quiz, we might not have that second term. If you look at the solution is already out as well. But basically, all it does is that if I go back here, there's some of scenarios such as, for example, this one, where instead of waiting for this instruction, we could have easily forward from here to here, right, and then continue, right? So what we would have is we have add-I that goes to fetch, decode, execute, memory, and write back. Then ORI. Then ORI would be fetch, decode, execution, memory, write back. Then we have the AND-I, which dependent on the add-I. So we have the fetch, we have the decode. And in the previous case, we were stalling the processor for one cycle because we didn't have forwarding. But now we can have forwarding between here, between here and here, right? Because the results of the add-I can be forwarded to our AND-I, and then we can just continue our execution, right? And this would be our AND-I, right? So we're kind of like saving one cycle here by just doing the forwarding from write back to the execution stage. And we ask you to add star or asterisk or something like that to show that there is a forwarding, and the forwarding happens from whatever that cycle is to the execution stage. Does that make sense? Does this notation make sense? Yeah. So the question is that do we still need half cycle for this or not? Anybody wants to answer that? Any takers? Yeah. Yeah, so the answer is we don't need half cycle because the forwarding is, if you look back at your design, the forwarding was basically this wire that coming out of our pipeline register, and we were putting this back into that mux here, right? So we're not reading from the register file saying, oh, we need half cycle. The forwarding was happening literally from that wire we took out from the write back stage and putting back. So there is no writing happening that whether we need half cycle or not, because we just, before even writing to a register file, we are forwarding that. Does that make sense? Okay. Then we have sub, right? So so fetch happens here. Since now this has moved to the execution stage, this can safely goes into the decode. Do we have any? No, we don't have, but that's where the half cycle actually happens here. That we have the execution stage, because this decode and this write back happens at the same cycle, but since we have the half cycle, this is a safe thing to do, right? So the half cycle actually, that's where the half cycle is helpful. Execution, memory, and write back, right? And then we go to the load. Load happens here, decode. Do we have any? No, we don't. So let's continue, right? Then we have that tricky add and tricky branch. So the add one goes here, decode. This is where we cannot have forwarding. Anybody say why we cannot have forwarding? Why forwarding doesn't work here? Because we have a load use, right? So load use, you need to stall for one cycle. And then at this cycle, you will have your execution in memory. And where does the forwarding happens? From here to here, right? So because at the end of the memory cycle, we have the value for load, so we can only forward it at the beginning of the write back stage, right? So that would be the forwarding that happens for the add. Any questions here? And then we have the branch. The branch would be F. It cannot move forward, so it would be F here. Then it would be D. Then it has to wait all the way for this add, if I remember correctly, right? So it goes into this E here, right? Because we can forward from here to here. Then goes mem, and then goes right back, right? So we are forwarding from the add to the branch, right? And then finally, before that mul instruction, we will have fetch here, decode here, and then we realize this is a branch at this point. So we're not gonna fetch another thing here. We're gonna keep this at the fetch, and then stays at the fetch, and then at this point we're gonna say that this is safe to move forward, and this would be decode, execute, and so on and so forth, right? So remember, this is a branch, has nothing to do with forwarding, and we only do it at this stage. Although in this specific question, we said that we know the results in the decode stage. So in that case, we only fetch, we stall for one cycle instead of 3 cycles, okay? That was the difference. But again, for your specific case, since we don't talk about moving things to the decode stage in lecture 7, you always assume that your branch is resolved at the end of the memory stage. Does that make sense? Yeah. So your fetch is here, right? And then this is a branch, so you cannot move forward with decode, right? So you have to stay at the fetch, and then you have to stay at the fetch again, because it's the memory. At the end of the memory cycle, we know that this is a correct results, right? So 3 cycles we need to wait for our branch in our original design, right? This is a branch instruction, and we need to, by the end of the memory stage, we know what the branch instruction is. So at the beginning of the write back stage, we know that the correct address for the fetch. We are doing the assuming is not taken thing. Yeah, that's why we're saying, so that's why if it was ORI, then it could have just go easily forward. Now, because it's the taken one, it's this one, it has to wait. From M to F. So the question is why there's no stall. What are you gonna? Oh yeah. Sorry. So you have to do fetch here and decode here. Yeah, you're right.
from the to code state.
So the question is, why are we not forwarding from here to here and not to here, right? So why not to decode? Remember, we are talking about the old design where our comparison was done inside the ALU. So we need to forward to ALU. That was the story when we moved everything to the decode stage, and then we had the forwarding. It's a little bit confusing because now you know more and you kind of like confuse these things. I'll probably like make it sure that you know what happens when, or just keep in mind, I'll make a big notes that you know this is the scenario. Because if we had the newer style where we moved we had a comparator after the register file, then you had to forward back to the decode stage. But this is not the case here. We are doing a normal pipeline stage where we have our you know register file here. We had our pipeline registers, and here we had RS1 and RS2. And these are the incorrect RS1 and RS2. We read a wrong thing in the decode. So we add this multiplexers and forward things back to our ALU, right? So that's what I'm saying. So for your normal scenario, I mean, for this specific question, yes. What I'm saying is for you, given that you don't know that additional information, this is the correct way of solving this problem. Okay, does that make sense? So the question is, why don't we forward from here to here? What are you going to forward? Piece here is the PC, it's not RS1 and RS2, right? So forwarding for branches doesn't help. What helps for branching is knowing what is the next PC, right? So for branching, we don't have forwarding at all because forwarding doesn't make any sense. Forwarding is for RS1 and RS2 and RD, not for PC, right? Yeah.
So in this, we're not doing the assuming that the output of branch is not.
Yeah. Yeah, the question is in my solution, I'm not assuming that the code is. If you go out and look in the website and see the solution there, we actually assume that the decode has been resolved. So that's why you don't need to wait 3 cycles, you just wait 1 cycle. In this one that I'm showing here, I'm assuming that your branch is resolved in the mem stage, and that's why you have to wait. And what I'm saying is that in your quiz, you have to make this assumption unless I say something otherwise. Yeah. Mm-hmm. Oh, so the question is, can you do from here to here, right?
Yeah.
Yes, you can do that. The reason that we are doing it this way is in reality, this is the instruction that has the hazard. So it's better for readability to do that. You can technically do this, but if you actually, the way that the hardware going to implement this is that's going to forward it from here. So if you do it that way, it would be wrong. Okay, are we good? I don't have branch M to F. Somebody ask it and say, no, we cannot do it. Yeah. Okay, so just a few more things to know is that other than kind of like having kind of a good idea about your pipeline, the other things that you'll probably see in the quiz is like, you know, redesigning your data path controller. Maybe we add another instruction and want you to make changes. Just have a fairly good understanding of like what are the units that are being used for this instruction and the other instruction, what are the costs associated with each of them, how do you calculate the propagation delay from the beginning to the end, that question that we had in the homework, and then have some basic understanding of the opcode, the ASM, how do we transfer or translate from binary to machine code, sorry, from machine code to assembly and other way around. Have a good understanding of the iron law and all the three things and what happens if you do this and that. We might ask questions like that. Design of the pipeline, have a good understanding of all these things and what happens when do we know the outcome of the branch, when do we know the forwarding and all those things. Of course, you need to know about forwarding and hazards, the stalling, and generally the trade-off that we discussed in the class. Like, okay, we say, oh, we do this is the trade-off, we do that, that's the trade-off, and so on. Okay, that's it, guys. Good luck.